Welcome to our first talk of the year for our public lecture series for this school year. My name is Willow Reed. I'm a communication specialist here at LASP. And today I am excited to welcome Dr. Bruce Jakosky to give his public lecture. Dr. Jakosky is a senior research associate here at LASP at the University of Colorado Boulder. And Dr. Jakosky came to LASP in 1982 as a postdoc and worked under the former director of the lab, Charles Barth. Dr. Jakosky's research interests are in geology of planetary surfaces, the evolution of the Martian atmosphere and climate, the potential for life on Mars and elsewhere, and the physiological and societal issues in astrobiology. He has participated in many spaceflight missions over the years, including Viking missions, the Solar Mesosphere Explorer, Clementine, Mars Observer, Mars Global Surveyor, Mars Odyssey, and Mars Science Laboratory. You'll see there's a theme. He was the principal investigator of the Mars Atmosphere and Volatile Evolution, or MAVEN, mission to Mars from its inception in 2003 through 7 years of operation in orbit at Mars, stepping down last fall. He was also a professor at the CU Department of Geological Sciences from 1988 to 2021, and has been heavily involved in planning the future program of robotic exploration of Mars. He has published more than 300 papers in refereed science literature and authored a number of books on planetary science. In addition, he was the sole author of The Search for Life on Other Planets and Science, Society, and the Search for Life in the Universe. As evidenced here, Dr. Jakosky is a leading expert in all things Mars, and I'm looking forward to tonight's presentation. So thank you, Dr. Jakosky, for joining us, and I will hand it over to you.
Thank you, Willow. Can you guys hear? And are we good online? First of all, thank you for letting me give this talk. I had to come and twist your arm to let me do it. And I'll be honest, I'm a little bit nervous tonight. This is about the first talk I've given in person in several years, and it's a little bit daunting, especially because I see some of my professional colleagues in the room. So to the several of you, they know more about some of what I'm going to talk about than I do. So if I say anything that is at all incorrect or misleading, please feel free to just keep it to yourself. I want to talk tonight about the possibilities for life on Mars. Mars is a hot topic. Everybody seems to be talking about it these days. And the main theme seems to be, is there life on Mars? Was there ever life on Mars? And if you follow the news and what Elon Musk says, and I try not to do that, but it's hard to miss him, are we going to terraform Mars and send people to Mars within this decade? Those are the topics I want to talk about. This question of life really has become the overarching theme of Mars exploration. It is dominating the exploration, the sending of spacecraft, the issues we're trying to address. We have several spacecraft there right now that are looking for evidence for life, or will be bringing rocks back to look for life. It hasn't always been that way. I remember when I started in this field, and Carl Sagan was big on looking for life. He was sort of pushed aside, and geology was where it's at. Geology is still where it's at, but life has become pretty central. The questions I want to really think about: has Mars ever been habitable? And by habitable, I mean, could there be microbes there? I don't mean bunny rabbits or camels or people right now, but are there microbes there? Have there ever been microbes? Has Mars ever had life, and how are we searching for it? Are humans going to go to Mars? Are they going to go within our lifetime? And how are we going to do that? Can we terraform Mars, make the environment look more like the Earth's environment so we can walk around without spacesuits? And at the end, I want to come back to, why are we exploring Mars? This is one of the real issues in my mind, not just that we are doing it, but what it is we hope to get out of doing it. I threw up here just some different pictures of Mars over the years, going back to the canals 100 years ago and terraform Mars 100 or 1,000 or 10,000 years from now. If we're going to talk about life on Mars, we really need to start with a comparison with the Earth. Earth is the only planet we know of in the universe, really, that has life. And we need to understand the nature of life on Earth if we're going to understand the possibilities for life on Mars. Mars, by the way, is the one on the right. It's about half the diameter of the Earth. It resides about 1.5 times as far from the sun as the Earth is, and it has a much thinner atmosphere, only about 5% as thick, excuse me, 0.5% as thick. What's a factor of 10 among friends? 0.5% as thick as the Earth's atmosphere, so it's a lot colder. But we really need to start with the Earth. Everything we see in this picture tells us how wonderful Earth is to support life. It's got water. You can see the green from plants. You can see the brown from desert. It's got a thick atmosphere. If we want to learn about life on Mars, we start with Earth. And the piece of it that I want to focus on to start with is the extremes of life, because Mars' environment is very different from the Earth's environment. It's a lot colder. It's a lot drier. There's not oceans. And we need to think about how extreme an environment life can reside in and still survive. And I picked some examples of the most extreme environments on Earth in which life resides and in fact thrives. And if you've ever been to Yellowstone, you'll recognize this one in the upper left. It's the Grand Prismatic Spring. All of those colors, and by the way, if you can't quite see it, there's a boardwalk along the back with people on it, give you a sense of the scale. So this is maybe 75 meters across. All of those colors represent different organisms that live in the hot springs. The water is coming up at boiling temperatures from below. It's heated by deeply seated volcanism. And as it comes up, it can cool off and flow outward. And that creates this bullseye pattern of different colors living at different temperatures. These organisms really like to live in hot water. And in fact, if you take them to room temperature, which is what we like, they die. They can't survive in such a cold environment. On the other hand, these things that are called cryptoendoliths in Antarctica can survive in low temperatures. Cryptoendolith means it lives in a rock and we don't understand it. That's the crypto. Just like cryptocurrency, that means we don't understand it. We're looking at the cross section of a rock here that was picked up off the surface. This is actually about 1 centimeter high. The surface is up at the top, and this dark streak in the middle consists of organisms. And they like living inside the rock because liquid water can survive there, even though the temperatures in the air never get up above about 245 Kelvin. That's, geez, I can't do the math in my head on the fly here. That's about minus 18 degrees C. And organisms can do quite well in that environment as long as they're protected. My other favorite are these radiation-resistant bacteria. By the way, if somebody knows how to get rid of this bar across the bottom, please tell me and I'll do it. Thank you, Willa. These radiation-resistant organisms have figured out a way to correct the mistakes introduced in their DNA and their chemistry by the radiation. The radiation breaks the bonds. These have figured out how to live in there. They were discovered living in nuclear reactors in the core. We don't think they evolved there, thank you. We don't think they evolved to live there. We think they evolved to live in a very dry environment where the dryness, the desiccating environment does the same thing as the radiation in terms of breaking chemical bonds. And this other thing that looks like an ashtray isn't. These are tube worms that live at the bottom of the ocean near spreading centers where hot water is coming up from beneath. Again, they live in water at temperatures above the boiling temperature at the surface here, but they're buried deeply, so they do fine. And it just shows the wide range of environments in which life can exist. So even though Mars may not have an environment today that looks like what we're used to thinking of for life, don't rule it out because life can live in a wide range of environments. And in fact, when we look at life, we begin to understand that the requirements on the environment are really pretty simple. We require all of the elements, access to the biogenic elements, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, calcium, iron, manganese, magnesium, and about 20 others that I can never remember. You're going to find these on any geologically active planet. You can find them in the rocks. You need a source of energy to drive metabolism, to drive chemical reactions that look like metabolism. And that source of life, source of energy on Earth is the sun for almost all organisms through photosynthesis. Plants are photosynthetic. We aren't, although I think that would be cool if we were, just go lie out on a rock and get energy. But we eat plants, and sometimes we eat animals that eat plants. There are a few organisms on Earth that get their energy out of chemical reactions from the environment, like the reactions between water and rock. We think that may have been the first source of energy to drive metabolism. And we need liquid water. We need water as a medium in which everything can exist, as something through which nutrients can flow into an organism, waste products can flow away from it. We're going to look and see if we meet these requirements on Mars. I'm going to spoil the whole talk and tell you that we're going to, but you'll see how. But let's start, finally, Mars. Let's start with Mars today. It's a cold, dry place. Temperatures average about 60 degrees C below the freezing temperature of ice. I guess the freezing temperature of water, below the temperature of at which water can exist. It's a temperature at which you really don't expect to find water in any significant amount, trace amounts, a few molecules here and there. You don't expect to find organisms living. These are two pictures from different landers, both of them showing what looks to me like very much a desert scene. On Earth, the weather is dominated by water. You go outside and all the atmospheric motions, all the clouds, all the rain. On Mars, the weather is dominated by dust in the atmosphere. And I picked a few examples here with dust devils that are small. You've all seen dust devils, maybe 5, 10 meters across. We're looking down on it here from above, so you can see the dust devil itself and the shadow it casts. We see small-scale dust storms that are localized in size and extent. The edge of the dust storm is around here. And we see global dust storms. Dust seems to dominate the atmosphere on Mars. That's very different from the Earth. There is water in the atmosphere. Most of it is present as water vapor. You can't see the water vapor, but you can see the clouds here. The amount of water vapor in the atmosphere, this is what I've spent most of my career studying, the water. If you condensed it all out of the atmosphere, it would make a layer about 1,000th of a millimeter thick. Very thin. For comparison, if you did that on the Earth, it would be about 15 centimeters thick. Lots of water. It condenses in places to form clouds because the atmosphere is so cold. And the clouds are solid crystals. They're not liquid water. We do see water more let's see if I can speak English in complete sentences. We do see much greater extents of water. For example, we see water ice frozen in the polar caps. This global image, you can see the polar cap up at the north. Close up, you can see this very complex geological environment. And even closer up, you can see what look like layers of water ice and dust, alternating layers, or water ice and dust mixed in different proportions. We also see what I'm calling massive buried mid-latitude deposits of ice. It's not really blue. Somebody likes the color the false color. Everybody colors water or water ice blue because it's cute. If you're struggling on this, if you're walking from the top, you're walking over a flat surface, you get to a scarp here, and if you take one more step, you fall down to the bottom. That's a few hundred meters, and then it's flat again. The term massive, I'm using it in the geological sense as dense ice without a lot of stuff mixed in. You do see some layering, but not in any great amount. Now, despite the present environment, we think that there has been liquid water on Mars in the past. We're not looking at the ice cap polar up close here. But on ancient surfaces, you see this pattern of channels that look like runoff of rainfall. You can see smaller channels coalescing into bigger channels as it flows downhill. It looks like a river drainage system. We know that this is one of the ancient surfaces because you can see the impact craters. They suggest that this surface formed about 4 billion years ago. So it's a very old surface. To have water like this on the surface, running off the surface, you must have had a much warmer environment than we have today, or a much wetter environment. In the middle epochs, we see what looks like flood features. You can see the channel carved by water. Note the scale bar in the upper left, 100 kilometers. That means this channel looks to my eye to be about 300 kilometers across, and it was pretty much filled with water at one time. Think of that as like the Mississippi in flood stage. That's a lot of water. And you can tell it was water because you can see these streamlined teardrop-shaped islands where water flowed around the obstacles. Here's a really good one. Here's another one here. You know, people ask me, why do I think it's water? Could it be anything else? People have suggested wind. They've suggested this being carved by a very fluid lava. One of my colleagues early on even suggested that it was produced by photochemically produced hydrocarbons that would have rained out of the atmosphere. In other words, think Wesson oil flowing over the surface. And I'm going to give you a very technical reason why I think this was water. And this is the most technical thing I'm going to say during this talk. But we think that this was carved by water because it looks like it was carved by water. Did I go too fast on that one? Should I try that again? That's also in the middle epochs. Also in the middle epochs, we're going to come back to this. We see impact craters that look like they were filled with lakes. This is Gale Crater, which is where the Curiosity rover is tootling around right now. And I picked this image because all this stuff up in the front here is mudstone formed when water filled the bottom and when the water evaporated. The chemistry, the geology, the layering, the morphology is convincing that this was formed by mud. And then the final example I'm going to use, this is a global map of Mars. All these colored dots represent where minerals have been identified using orbiting remote sensing. The minerals require liquid water to form. They can't form in the absence of liquid water. And all of these minerals concentrate on the heavily cratered surfaces, so they're very old, some of the oldest features we see. All of this, I think, is pretty convincing that we're seeing a lot of evidence for liquid water. So I'm going to come back to this chart. Do we meet the requirements for life? Access to the elements, you know, it's a geologically active planet. We measure the abundance of the elements. We seem to have everything we need. Source of energy, chemical reactions between water and rock do quite nicely, and liquid water. So I think we have met these requirements. And to me, that says it's now not a stupid question to ask if there could be life. Mars meets or met at some time in the past the requirements for life. So let's talk about the search for life on Mars. We sent the Viking spacecraft in the 1970s. This is actually where I got my start in science as an undergraduate working on the Viking mission. We did not send Carl Sagan. He just posed with it on the Earth. The goal of this mission was to look for evidence of life. And this, I still think, is one of the most dramatic images we've ever returned from Mars. It's a wide panorama showing the area around the lander. This turns out to be one of the rockiest places on the planet. But you look at this, you don't see any evidence for water. You see evidence for windblown dusts and drifts, for rocks, If you're a geologist, you can look at the shape of the rocks and infer that the wind has carved it out, has created this, what's called a vent effect. So we know that wind has been active. We don't see anything here that looks like water. So Viking carried with it 3 experiments to look for life. And I'm not going to go through this in detail, but these experiments were designed to look for different ways in which life can operate, different pieces of evidence to show whether there was metabolism. How is carbon taken up? Is it taken up? Can it be taken out of the CO2? Can it be taken out of nutrients? And if you add nutrients, does it give off gases? On Earth, all of these things are indicative of the presence of life. Each one tests for a different style of metabolism. What's interesting is that each one of these experiments initially returned a positive response. It returned the response that you would expect if there was life. So they did a control experiment. They heated up the sample to temperatures that you would expect would kill things and did it again. And 2 of them, the first and third here, still gave the same response, suggesting it was chemical reactions rather than life. The third one, the labeled release experiment, gave this result. And let me walk you through this. In the first experiment, they added nutrients and they saw the release of carbon, of CO2 into the atmosphere. They could detect it. That's what you would expect if there was life. After they heated it up, they did it again, nothing. So the conclusion reached by these investigators was they met the criteria for life. They were seeing life. But it's not as simple as that. It never is. If they were seeing life, and if it was carbon-based life, which you're looking for carbon, you would expect to find organic molecules in the soil. Organic molecules are just, think of it as carbon and hydrogen combined together in different ways. There was an experiment to look for that. It was called a mass spectrometer. It measures the mass of stuff coming out of the soil. And they looked and they found none. Actually, that's not quite true. They found the organic molecules in trace amounts that had been used as solvent to clean the instrument at really low levels. It was a damn clean instrument. But they didn't see organics at the level that would have been necessary had the labeled release experiment been looking at life. So what's the bottom line here? The investigators on the one experiment lived out their lives. They recently passed away, unfortunately, thinking that they had discovered life on Mars. The science community doesn't accept that. They think that collectively, all of this points toward chemistry. It doesn't rule out life. Life is really hard to detect, and it's really hard to grow remotely. So I think we're left with, I don't know, hard to tell. The second way we've looked for life is with meteorites from Mars. And in particular, one called ALH 84001. It just rolls off the tongue very quickly once you said it 10,000 times. This is a picture of it on the left. Here's a centimeter cube for scale, so it's about this big. I have never seen it. It's locked up in a vault at the Johnson Space Center. They go to Antarctica now and collect meteorites. And the reason they go there is you go out on the ice sheet, and if you find a rock, how the hell did it get there? It must have fallen out of the sky. Unfortunately, they didn't take a picture of them collecting it. By the way, the name comes from the expedition in 1984 to the Allen Hills region of Antarctica, and it happened to be the first rock they picked up. They didn't take a picture of it, but I wanted to show a picture of collecting a rock, so this is it. Most people are surprised that we have meteorites from Mars. And I put in a picture of my sample here, and I brought it with me if anybody wants to look at it afterwards. You may not take it home with you. You may not taste it. These meteorites are absolutely convincingly from Mars. They're young volcanic rocks, and the composition is compelling in telling us that it came from Mars. It has gas trapped within it that is identical in composition to the Mars atmosphere. If it's not from Mars, then we don't know anything about our solar system. I bought this sample when I became convinced that these were Martian. And when I bought it, the going rate was about $100 a gram. And I figured that is so much more cool to have a piece of rock from Mars, way more cool than what some of the people here in Boulder would spend $100 a gram for. Now, you can buy these from dealers. That's where I got this one. You can also buy other things from dealers. This is a ring. It's actually an engagement ring that you can buy. The cost for this ring, mainly from the gold and the diamonds, is about $30,000, if you can believe that. And as much as I'm a Martian, I cannot imagine coming home to my significant other and saying, I got you an engagement ring with a 10-carat rock in it, and then coming up with this. We'll leave it at that. The evidence in the Allen Hills meteorite for possible life, there were these things that showed up in electron microscopes that look like fossil organisms. They found layering within the rock. You can see the layers in these different colors, the brown, the black, and in some cases, little slivers of white, indicates disequilibrium that could be produced by life. And there are perfect magnetite grains here that I've circled on the right that are very similar to magnetite grains produced in terrestrial microbes. Their argument was each one of these could have any one of a number of explanations. The common explanation that would explain all of them would be life. It took 5 years and 500 different laboratories around the world to really begin to understand that. What's the bottom line? All of these features are either artifacts, this is my view, not everybody's view. They're either artifacts of the processing of the rock to look at it, like this thing, or they're evidence that hot water flowed through the rock while it was still on Mars. So it's telling us probably nothing about life itself, except it does say with that hot water flowing through the rock, this is a great place that life could have lived. We don't know what's really there. So I don't think people are convinced that this is evidence for life. The final evidence, the final piece of the search is ongoing today, and that's going to be going to Mars, going to a place where they think life could have existed, where liquid water was long-lived, going to rocks that would retain a memory of that life, picking up samples and bringing it back here to study on Earth. You just can't do enough analyses remotely on a spacecraft to really be convincing one way or another. We need to bring the rocks back to Earth. So we've sent the Perseverance rover. It's operating on Mars right now in Jezero crater. This is a self-portrait of it. It's been operating, boy, I can't remember, a year and a half now, I think since February of last year. And it's doing wonderful things. I keep reading in the papers every week about new discoveries. It landed in Jezero crater. It's about a 50-kilometer across crater. Here, the colors represent topography, not water, although this was thought to be a lake. You can see where water flowed into the lake on the left, where it flowed out of the lake on the right. That red box we're going to look at closer up here. This is where it landed. This thing here is a delta deposit where water carrying sediment flowed into standing body of water, and all the water slowed down, all the sediment dropped out, and it created this delta. Again, very similar to what we see on Earth, very well understood. Scale bar up there, 10 kilometers. Perseverance has gone about 10 kilometers, and it is doing analyses as it drives around, and it's collecting samples that we're going to bring back to Earth. Most recently, about 10 days ago, if you read the paper, Perseverance discovered the greatest abundance of organic molecules it's found. And that's a really big thing, because organic molecules would be present, could be present if there had been life there. It doesn't require life, though. Organic molecules can be produced by non-biological processes, and they can also be brought in by meteorites that come in. So we need to bring that sample back and analyze it here in the lab. They've collected a sample of that, and that's one of the high priority samples that would be brought back. So you look at this picture, this is the whole sample return scenario. There's Perseverance. We're going to send a lander that's going to collect the samples Perseverance is picking up. It's going to put them into a container. It's going to be launched into orbit, and a spacecraft is going to bring it back to the Earth. Sounds really simple. This is the hardest thing we've ever done. I believe harder than James Webb Space Telescope, harder than Hubble Space Telescope, more expensive than James Webb Space Telescope, more expensive than Hubble, but the science is spectacular, and I think it's going to be an important result, whatever we find, whether we find evidence for life or not. So that's the past of life, the present search for life. What about the future of life? Let's talk about human missions to Mars. Pardon my modifying a well-known cartoon, but to go from the current robotic program to the first human mission, we sort of need a miracle. And the miracle is a commitment from NASA and the US government to do it. We have the technical capability. There are no showstoppers. We just have to be willing to spend the $100 or so billion it takes to do it, spread out over 20 years or so, and to take the risk with people. You know, when we send people to the moon, if they get in trouble, they're only 3 days from coming back. If we send them to Mars, if they get in trouble, they're 6 months, at least 6 months, maybe 9 months if they get into trouble just after they start to Mars. So how are we going to do this? I'm very fond of Lockheed Martin's concept they call Mars Base Camp. It uses their Orion spacecraft. It has one right here with all the support structure. There are 2 of them, one on each side because you want some redundancy, and then crew compartment in the middle. We could build this today. It's very straightforward. It could take us to Mars, put us into orbit, take us back. This particular structure would not be able to land. We'd have to do a separate lander. That would be pretty spectacular. Now, Elon Musk thinks he has the lander. It's his Starship. To listen to him, he's designing it in order to go to Mars. He wants to send people to Mars. He wants to populate Mars, put a city there. By the way, I'd like to send some people to Mars too. I'm just not going to name names tonight. These are artist rendition. He hasn't gotten it into Earth orbit yet. But then we haven't gotten Artemis into Earth orbit yet either. But we're on a path with both of those. Are we on a path to have outposts on Mars? If you've seen the movie The Martian, you know what I'm talking about. Who's seen The Martian? God, you guys are all Martians. You know what I'm talking about. It's not impossible. It's very straightforward, not trivial, but very doable. What about cities on Mars? The big question I would ask would be why? Mars is a horrible place to live. I read a description by one of my colleagues that said, if you want to go to Mars, spend a year up on top of Mount Everest first. And as difficult an environment as Everest is compared to here, Mars is that much more difficult than Everest. So it's going to be a difficult task. Okay, let's look farther into the future, far enough into the future that we can't predict what's going to happen. Can we terraform Mars? Terraforming means changing the environment, putting gas in the atmosphere that would raise the temperature to the point that liquid water might be stable, and perhaps people could live on the surface. To do that, we might look for something like CO2, which is a very efficient greenhouse gas, and see if we can put it in the atmosphere. This is something that Elon Musk talks about endlessly ad nauseum. This is a quote of his from a few years ago. You need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on. Now, I think he's talking about without a spacesuit. I don't think he's talking about Martian nudist colonies, but With Elon, you can't be sure. He calls it a fixer-upper of a planet. You know he's serious about it because he has a slogan, Nuke Mars, and a t-shirt. And if you have a slogan and a t-shirt, you're halfway there. So one of the things that our research group has been doing is looking to see, can we terraform Mars? Can we find enough indigenous materials, really meaning CO2, that it would warm up the atmosphere? And we've looked at where you might be able to find the CO2. You can find it in the polar ice caps. We know there's some there. If you put that into the atmosphere, it would double the atmospheric pressure, still not very high. We can find it in the ground where it's bound by a process called adsorption. We can get maybe a couple of tens of millibars, maybe a percent as much gas as we have in the Earth's atmosphere. And again, not very much. We can look for carbon-bearing minerals, carbonates, that are locked up in the surface. There may be a lot there, enough to do this, but they're distributed globally and they may be buried very deeply. You'd have to strip mine the entire planet and heat it up to get it out. Not feasible. We think that a lot of the carbon has been lost to space. And once it's lost to space, you ain't never getting it back. Now, if you really are patient, you can wait for continued volcanic outgassing to replenish the atmosphere. I think you'd have to wait about 3 billion years to do that. But why not? Start now. Set your calendars. So can Mars be terraformed? I think the answer is probably not. There just isn't enough CO2, and the CO2 that is there can't easily be mobilized in order to put it into the atmosphere. All is not lost, however, because we can always imagine that we can create designer molecules that would be a very efficient greenhouse gas. Think of things like chlorofluorocarbons, like Freon, that would be a very efficient greenhouse gas. Mars has all the ingredients. It has the carbon, it has chlorine. All you need to do is build a factory and manufacture it. Of course, that factory would have to be bigger than anything we've built on Earth, and we still haven't sent anybody there. So I think that's still in the realm of science fiction. I don't want to sell Elon short totally. I think his vision is very powerful, and he's outstanding as a visionary. And I put a quote here that exemplifies the power of Elon Musk's vision. If you want to build a ship, don't drum up people to collect wood and don't assign them tasks and work, but rather teach them to long for the endless immensity of the sea. And I think that's what Elon is doing. He is building up excitement and interest in going out into space, in going to Mars. And I think that has very positive effects. On the other hand, there's a danger in his vision from this seen in this Calvin and Hobbes cartoon. So long, Mom, Hobbes and I are going to Mars to live. Earth is too polluted. If we think that Earth is a disposable planet, that we have a backup planet, we won't take care of our own planet. And I guarantee you, no matter what we do to the Earth, it's going to be easier to fix the Earth environment than to go and get Mars environment to look like ours. So the last part of the talk, I want to talk about the significance of finding life on Mars or elsewhere. Now, we're going to Mars to look for life. I see too many NASA charts where it says that we're going to Mars to find life. We're going to find out if there's life. But if we did, what would be the significance? You know, we have clues because we have this Mars meteorite that initially was announced as having evidence for life. It made the front page of the New York Times, 1996, above the fold. Then President Clinton talked about it at a press briefing. It really was exciting. I will say this isn't the first time the New York Times has published articles on life. This one goes back to, I can't read it, 1906, when Percival Lowell was talking about life on Mars. And if you can't read that secondary headline, Professor Percival Lowell, recognized as the greatest authority on the subject, declares there can be no doubt that living beings inhabit our neighbor world. 100 years ago, this was not a controversial issue. There was a planet it had an atmosphere. Of course, there would be life. Of course, there would be intelligent beings. Well, maybe not. You know, before I retired as a professor, I would ask my students in class, I taught a class on life in the universe, and I asked the students one time, what would it mean to find life? And their answers were so intriguing and across the board that I wanted to catalog them here. And I've reworded them, but these are all straight out of the answers the students gave me. So the first thing they said, finding extraterrestrial microbes won't make much of a difference to most people. Their lives will go on as before. It doesn't matter to most of us whether there's life on Mars or not. It doesn't affect what we do day to day here on Earth. I guarantee you my funding would go up, but that's a minor issue. Well, maybe not so minor for me. This is similar to when Copernicus, when Galileo recognized that the Earth goes around the sun rather than the Earth being the center of the universe. It didn't make a difference to most people. You'd be hard pressed to tell me why it makes a difference whether the Earth goes around the sun or the sun goes around the Earth. It's very subtle and not obvious. On the other hand, some felt that finding microbes would be scientifically interesting, at least to us pointy-headed scientists wearing white lab coats, but only finding extraterrestrial intelligence would be truly profound. I can't argue with that. I think it would be. I think that a lot of the interest in life on Mars, microbes on Mars, is pointed toward understanding life in general and whether there could be intelligent life out there. A couple of people we felt we should solve our own problems here on Earth before we go looking for life elsewhere. I wasn't quite sure why they were taking the class, but that's okay. No problem for me. Some people felt that extraterrestrial intelligence now would help us to solve all of our earthly problems. If you've seen the movie Contact, or I just recently watched The Day the Earth Stood Still from the 1950s, you know that they're coming here and telling us to get our act together and solve our problems. They're willing to help us. On the other hand, there are those who felt that extraterrestrial intelligence will destroy our civilization either by intent or by accident. If you've seen the movie Independence Day, who's seen that? So most of you have seen that. You know they're coming here to kill us. What I like about this is everything from one extreme to the other extreme. It's a litmus test on your view of the world, right? Based on no evidence whatsoever, rather than on some reality. Continuing, some felt that the existence of extraterrestrial life or intelligence would be inconsistent with modern religions, and it would bring the whole religious enterprise crumbling down. On the other hand, many felt that modern religions have dealt with scientific discoveries and societal changes in the past. They should be able to adapt. And in fact, if you listen to the academicians who study religion, they'll tell you there's not even a conflict. A number felt we've already discovered extraterrestrial life. The government is hiding it, probably in Area 51 or near Roswell, New Mexico. And this next one really was there, but I'm struggling to understand what the student actually meant by it. We may not have discovered it yet, but the government's covering up anyways. How do you argue with that? I think that I come back to this quote from Arthur C. Clarke that I really like. There are two possibilities, and he's talking about intelligent life here. Maybe we're alone, maybe we're not. Both are equally frightening. It would be truly amazing to find evidence that there was another example of intelligent life. I do count us as intelligent. We'll find out over the next few decades if that's fair or not. But it would be truly amazing to find other intelligence. It would be just as amazing, if not more so, to search the entire galaxy or beyond our galaxy and find no evidence for life and realize we were alone. And this is my last chart. It's a quote that I love to come back to from T.S. Eliot. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. We're interested, now I'm going to put my spin on this. We're interested in studying the planets because we live on a planet. We want to understand how our planet works. And by looking at the other planets, we understand more about the processes. We're interested in life on Mars or Europa or on planets around other stars because we're trying to understand our own existence. Understanding the nature of life more generally than just on our own planet tells us about who we are as individuals, as a society, as civilization, as earthlings. One of my students put it very aptly, we're looking for ourselves. And I think that sums it up. We are the first generation that has a real chance of finding out if there's life elsewhere. We are not the first generation to say that. But counting today, we are the first. And we might find it from the Perseverance rover. We might find it from studying planets around other stars. If we could study plants around other stars, that would answer it right there. There are people who are listening with radio telescopes and may detect signals coming from life elsewhere. And I'm going to end with this quote that I've bastardized from John Muir: "Mars is calling and we must go." Thank you.
Thank you so much, Bruce. All right, so we're going to alternate questions in the room and online. So Terry, you want to start with an online question, and I will find any hands raised. I saw you first.
Yeah, I'm combining two here. The first is, what is dust on Mars composed of, and how big can dust storms be? Are they comparable to those on Earth?
Dust on Mars is composed of, think of it as broken up and chemically altered rock. If you go to Hawaii, this is an assignment for those of you who are students. You need to do this. If you go to Hawaii and pick up the red dirt, that's heavily weathered basaltic rock. Think of that as very similar to the dust on Mars. The size is different. The particles of dust on Mars are about the same size as the particles in cigarette smoke. So really, really tiny. Dust storms. We have global dust storms every couple of Mars years, every 2 to 4 Mars years. One will encompass the entire planet and shroud it from visibility. We don't have that on the Earth because the rain will wash it out. We do see dust storms that are significant on Earth. They come up out of the desert. The wind can pick up dust from the Sahara. It can blow it all the way across the ocean, and we can see it here. But we don't see any global scale dust storms like on Mars.
Hey, Michaela Huffman. I'm a first-year grad student.
While you're asking, can you take your mask off?
Oh,
It
yeah.
makes it a lot easier
You're
to
good.
understand.
I'm Michaela Huffman. I'm a first-year grad student in the APS department. I'm working with Dave Brain on how impact cratering affects atmospheres. And I was wondering, just personally, do you think Mars was episodically warm and wet, or was persistently warm and wet for a long period?
First, what I think doesn't matter. What does the evidence tell us? And I think that's one of the ongoing debates. You're going to be around next week. You can come to my last seminar next Thursday, where I'm going to talk a little bit about this. And in my view of the evolution of the Mars climate, we see a continuous gradation in climate, but that doesn't mean it hasn't been episodic. There are things that can drive episodic changes. So how's that for a non-answer?
Well, I guess we'll see you on Thursday.
Another online question is, we're looking for life on Mars relative to Earth. What if life on Mars is different from what we regard as life here? Do you think we first might need to redefine what life could mean on Mars and then search for those signatures?
That's a really good question and a really hard one for me to answer. For example, I know that there are people that want to send instruments that can detect DNA and RNA to look for life on Mars. the odds that they will have come on this, stumbled on the same solution to the chemical problems as Earth are small. So that's a very Earth-ocentric view of how to look for life on Mars. There are people who are developing ideas of what they call agnostic life detection that don't require as many assumptions about the nature of life. You would look for things like patterns in organic molecules. You would look for physical structures. I think that's our best bet. Right now, people are putting a lot of effort into what it might look like, but it's really hard when all of our examples of life are terrestrial. And all of life on Earth is genetically related to each other. So it all shares DNA, RNA, the same proteins, et cetera. How do you imagine what could be different? I think we're going to have to see it and find out. In many ways, it's going to be analogous to the Allen Hills meteorite experience, where until we got that meteorite and someone put forward, here are measurements that they think are due to life. Until we saw that, it was not possible to examine that. And I think when we get samples back, we're going to be looking for clues and then trying to understand processes, whether biological or not, that could leave those clues behind.
Hi, so I think a lot of people here probably know the answer to my question, but I don't, so that's why I'm asking it. If there used to be microbes in water, and I'm gonna guess a stronger atmosphere too on Mars, what happened to change that to be like it is now?
That actually is what I do in my own research. I'm studying the history of the Martian climate, the history of the gases. We sent a spacecraft called MAVEN to look at the role played by loss of gas to space, something which had not really been measured. But we see places where the gas could have gone. A lot of it has gone to space and escaped from the planet. Some of it has gone into the ground. The water can form hydrated minerals. The CO2 can form carbonate minerals. Some of it is bound up as ice in the polar caps. And if you add up all of these different places where CO2 or water could have gone and can be identified as having gone there, and how much is there, you get enough of each to explain that early atmosphere. So we're beginning to understand where the gas has gone. It's not a single answer, it's 5 answers for each of water and CO2. But in a nutshell, it can go up to the top of the atmosphere and be lost to space. It can go down and get buried in the subsurface.
And we have a question from the Philippines. What's the current evidence that suggests the presence of life now on Mars?
There is none. We have no evidence that is best explained by the presence of life. That doesn't mean there aren't people pointing to evidence. You know, we looked at the labeled release experiment on Viking. The investigators thought that that pointed toward evidence of life. There are still investigators working on the Allen Hills meteorite that think that that shows evidence for life. The most recent intriguing result comes from the organic molecules detected by Perseverance. I haven't been able to see the details of what they've measured, except what I read in the press releases. They haven't published their paper yet that I've seen. But in the press releases, they talk about detecting organics in greater abundance than has been seen before. That's awfully intriguing, but not by itself an indicator of life, because they can have other mechanisms of forming them. So there's nothing that is uniquely indicative of life. There's no evidence for which life is the best explanation. At best, life is on an equal footing with alternative explanations. And there are many people, if not the majority of the science community, that thinks those other explanations are better right now. We don't have the data. That doesn't mean we shouldn't keep looking for it. The way I think of it, you know, some of my colleagues say, we've been to Mars, we've looked for life, let's go somewhere else. In my mind, we've been to Mars, we've done experiments that were too simple-minded, we haven't really looked for life. We're not in a way that would find it if it was there in the amounts in which it might be there. So we need to go back and look for it.
So given the ongoing success of the Perseverance mission, Maven, Hope, and so on, and the upcoming retrieval of data and such, do you think that the success of that would be a big enough push to give us our miracle, as you stated, to really get the USA or the world together enough to go after that in a bigger fashion?
I think that if we found evidence that was widely accepted that there was life on Mars, that would push us over the hump and we would seriously plan human missions. There is planning going on for missions to Mars to follow the Artemis program to the moon. If you listen to NASA, they talk about moon to Mars. And Artemis, the goal of Artemis being to prepare for humans to Mars. I think it's going to happen, but it'll happen a lot quicker if we find life. Is that the miracle it'll take? That would do it. Sufficient, but is it necessary? I don't know.
Okay, another online question is, wouldn't terraforming Mars be futile since it would be stripped away by the solar wind over time?
Good question, but I don't think it's a problem because the stripping by the solar wind, which is what Maven was designed to observe, is happening at a very slow rate today. It happened at a much greater rate early in history. All the action was in the first few 100 million years when the sun and the solar wind were much more intense. So the rate of loss of gas today is something like 2 or 3 kilograms per second. And at that rate, I think it takes about 100 million years to remove all the atmosphere that is currently present on Mars. If we could terraform Mars, it would be stable. It would be there for the lifetime of the planet. But like I was saying, I don't think we can terraform Mars, at least not with current technology, not with indigenous materials. So in my mind, it's a moot question.
Thanks. It seems like you've made a distinction between terrestrial life and Martian life. And another thing that struck me from your talk was these asteroids or meteors from Mars that show up on Earth. There's a piece of it right there. So I'm just speculating about the possibility that life may have come from Earth to Mars. And could you comment on that possibility?
That's an absolutely fair question. We have transfer of rocks between planets. Here's a piece of one of the meteorites that has come from Mars. There are something like 300 rocks in our collection that have come from Mars. We have rocks from the moon. The current theories of how these rocks get ejected by an asteroid impact has them being not shocked and heated so much that were life living inside the rock, it would be killed. So you have the possibility of transferring organisms from one planet to the other. If we find life on Mars, the first question is going to be, is it a contaminant? Do we bring it ourselves? But after we answer that one, is it genetically related to life on Earth? Or does it represent an independent origin of life? If it is genetically related to life on Earth, did it go from Earth to Mars? Or could life have originated on Mars and been transferred to Earth? And that's a fair question.
And as a follow-up to that, someone online is wondering, if we did find microbes, would they be dangerous if they contaminated Earth? On the one hand, organisms from Mars are coming to Earth, if there are organisms on Mars, I don't want to assume, are coming to Earth in these rocks. So they've already visited. On the other hand, we have, as one of my colleagues pointed out, we have half a dozen global scale extinction events on Earth. How many of those were caused by Martian organisms? I think it's not an issue. On Earth, microbes that affect us, for example, affect us because they've grown up with us.
they evolved to be tuned to live off of us, to hurt us. Organisms that come from Mars would not have been with us, not for hundreds of millions to billions of years, and would not be tuned in that same way that they would be able to affect us. That said, when we bring these samples back from Mars, we're going to assume that they are hazardous, and we're going to put them in the most stringent facilities. Right now, we can deal with organisms like Ebola that are fatal 90% of the time. We work with them not me, others. We work with them in the lab all the time in environments where we take precautions. They can be dealt with in what's called a BSL-4 facility, biosafety lab, where the people wear suits that are protected. They don't come into contact with it. The only danger is if you're using a knife and you cut your suit, which does happen occasionally. But they take great precautions to ensure that it doesn't get out.
My son, Ethan, has a question. He's 6 years old, but he wants me to ask it for him. Why are rocks on Mars orange, but the ones that come to Earth are black?
That's a really good question. If you go to Hawaii, again, take this as an assignment for him. He should go to Hawaii and see for himself. If you look at the lava that is coming out, go out to a fresh lava flow. It's basalt that is coming from inside the Earth. It's black, it's dark. But if you go down to one of the beaches where the rock has been exposed for a while, it's reacted with water, it's reacted with carbon dioxide, it's chemically altered. And when it takes on the water, it turns into minerals that are red. They're reddish in color. Think of it as the iron in the minerals rusting. And that's a pretty good analogy. So it's the reactions with water. Does that help?
Great. We've got a couple questions related to water. What happened to the liquid water to make it disappear or be removed from the surface? How did it evaporate? And then also, what were some of the factors that may have caused Mars' atmosphere to lose the integrity it used to have to retain water?
Let's see, the water would have been at the surface, and some of it would have gone to the top of the atmosphere where sunlight would break it into the hydrogen and oxygen, and both of those can escape to space. The water can percolate down as liquid into the crust, into the soil, where it can react chemically with minerals and get locked up there, or if it goes a little bit deeper, where it might still be present as liquid water or as ice. What was the second half of that question?
And what happened to the atmosphere so that it evaporated?
I think all of these processes operate on Earth too, but the Earth has plate tectonics. So the water forms hydrated minerals, the CO2 forms carbonates at the bottom of the oceans, but the plates get shoved into the mantle where it gets heated up, and all that gas comes back out again in volcanoes. So we have this conveyor belt on the Earth that continually recycles stuff back into the atmosphere. Mars, as a smaller planet, didn't have that plate tectonics. It doesn't recycle the stuff. Once it's removed once, it's probably removed permanently. Fran, you can't ask questions.
I was just going to ask if you were going to let me ask a question, but if you don't want me to, I won't.
Go ahead.
Okay.
I'm in favor of sending people.
No, that was not my point. Bruce and I have actually taught a course about whether or not we should send humans to Moon and Mars. So we've had many, many decades of arguing together on this topic. So you have very carefully and beautifully described how Mars lost all its water billions of years ago. It's all gone, mostly. Europa has several Earths worth of water, most of it liquid under a protective layer of ice, which would be, and it's got tidal heating with volcanism inside the ocean, lots of nutrients coming out. So why are we wasting time and energy and money on Mars when we should be going to Europa and just focusing on Europa?
No, you can't ask a question. No, I think that's an absolutely fair question. And I have not said anything about whether there could be life on Europa. I think it is an excellent place to look for life. It meets all of those criteria that I had. You know, Mars, if we're going to get technical, I can point out the places where Mars might meet them today, but really it's in the past where those criteria were met with abundance. Europa meets them today. It's a fair question of could there be life on Europa? What I will say is Mars is easier to get to. It's cheaper to get to. You know, we've done approximately 30 spacecraft to Mars over the years that have worked. You know, I know we're up around a dozen US orbiters alone, plus half a dozen landers and rovers. I think we're up to 8 or 9 of them. And we haven't answered the question. It's a hard question. We've learned a lot about Mars, but it's taken us 30 spacecraft to do it. If we go to Europa, you know the answer to this. I can't do it off the top of my head. How many spacecraft have we sent that have looked at Europa? 3. We've sent 3 spacecraft, so we're a tenth of the way there. On Mars, we think we're only going to answer that question by bringing samples back. A sample return from Europa is incredibly hard. That doesn't mean we shouldn't be exploring Europa. It doesn't mean that let's see, how do I say this? It doesn't mean that we don't stand a chance of seeing evidence for life on Europa with Europa Clipper or the JUICE mission coming up, especially if we can fly through one of the plumes and detect organic molecules and quantify what they are. That's what I've heard some people describe as betting on the come. It's not necessarily the most likely scenario. I think we're going to Mars because it's easier, it's cheaper, and we can learn a lot more about it. And we've demonstrated that we have to know a hell of a lot before we can even try to answer that question about life. Now, we've learned a lot about Mars that we can apply to Europa, what some of the false positives might look like, what some of the mechanisms for producing organic molecules might look like. I'm not at all against searching for life on Europa, against missions to Europa, but that isn't where I think we should invest the money. Also, NASA has its stated goal of sending humans to Mars. You may or may not agree with that. I know the answer. It's unlikely we're going to send humans to Europa within our lifetimes, our children's lifetimes, our grandchildren's lifetimes. It's really hard to do.
So another online question, can you discuss the difficulties of soft landing humans given Mars' thin atmosphere and the 7 minutes of terror to slow down and land?
It's really hard. Oh, more detail than that. You know, Mars is an intermediate place, which is what makes it so hard. If we go to the moon, there's no atmosphere to speak of. And it's real easy. You have a 3-axis stabilized spacecraft. You're operating essentially in space, you land. Even though it's not a sure thing, it's not that hard. On Earth, we know how to land a spacecraft because it's got a really thick atmosphere. We can use it to slow down the spacecraft and land gently in the ocean on land. Mars is in that intermediate region where it's not thin enough to ignore and not thick enough to be useful. It's really hard. If we're going to send people, that's one of the hardest things to do is figure out, you know, we figured out how to land 1 ton. Perseverance and Curiosity are about 1 ton. It's really hard to figure out how to land 20 tons because that's heavy and it's doable, but it's not trivial. I fully understand the 7 minutes of terror. I also know enough in this inside baseball approach to know how close we've come to losing some of them because it's hard. And because Mars doesn't always do what we think it's going to do.
All right. Last question in the room. Awesome.
Hey, yeah, following up on that, if a spacecraft were to arrive at Mars and one of those dust storms kicks up, are they just random when they happen? Then do the 7 minutes even start?
They're not random. They occur at certain times. In fact, right now we are watching the rise of what's called a C storm, which is a regional dust storm that starts at this season on Mars just about every year. There's A, B, and C, and they all occur within well-defined times. We don't know why. And occasionally one of them will grow into a global dust storm. We don't know why. However, if you watch The Martian, the dust storm that stranded Matt Damon on the surface was unrealistic. It wouldn't really do that. The atmosphere is so thin that you have 100-mile-an-hour winds and you just stand there and you don't even notice it. You'd see all the dust blowing around, but it wouldn't knock you over. That doesn't mean it would be easy to land. In particular, those winds could kill you because when you're coming down through the atmosphere on a parachute, the winds are going to carry you along. And if you're coming down at 30 meters per second horizontally and you try to land, you're going to just go ba-dum, 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 ba-dum. And it changes the structure of the atmosphere. So the timing of when you use a parachute, when you transition to rockets, when you hit the surface changes. So it would be really hard. People are looking for the best times to go, which is out of dust storm season, but half the year is dust storm season, so it's 50-50. You're about to end it. Let me say, if anybody wants to come up afterwards and look at this piece of Mars, please do. I think the cool thing about it is being able to hold in your hand a rock that you know with absolute certainty came from Mars. And that's why I have this, just to be able to hold it. I don't do it too much alone in my office by myself, but I'm happy to do it here. But I'm going to keep a close watch on it because it's no longer $100 a gram. It's in the multiple thousands. So thank you for the opportunity to come and talk tonight.
Well, and thank you, Bruce. Another round of applause for our speaker, please.
Thank you.